There we go. Hello, my name's Robin Reed and I'm a postdoctoral research fellow at Plymouth University in the UK, and I work in the Centre for Robotics and Neural Systems. And so what we're looking at here is a little GUI application that can be connected to robots, and it's written in C++. And it uses the Qt libraries for creating the GUI and moving data around within the model. It uses OpenCV libraries to do the computer vision, so the image getting and then the actual processing of the images. And it also uses a third library called Aruco, which is really good for tracking AR codes. Okay, and so part of this video and talking about this is to show my coding skills, and this is going to be part of my CV portfolio. So, visual attention. Why do we want to give social robots visual attention? Well, there's lots of things in the world for robots to look at, and robots need to explore the world in order to learn about the world. Okay, very much like children do when they're growing up. They're always gazing around, looking at new, interesting and visually salient things in the world. And so you need to have mechanisms by which you allow the robot to explore the world and pick the things that it actually finds interesting to look at. And this is a proposed model of how you can do that. And it's proposed by Cynthia Beazeal, and it's described in this book, Designing Sociable Robots. But the implementation here is completely from scratch on my part. Okay? And so what we have is up here, this is the raw camera image for my desktop webcam. And what you do is you split this into very simple features, and we call this a bottom-up approach to modeling. So we take basic features and we combine them together. And our features here are motion, where you take consecutive images and you compute the absolute difference. And if that difference lies above a certain threshold, which we can set here, then we consider it motion. So the higher the threshold, the more noise reduction you effectively do. And the lower the threshold, the less noise reduction we do. We have here a skin map, which is just computing skin-like tones and saying whether or not it considers this to be skin or not. We have a color map, which looks for bright colors, basically the salient colors, the reds, the blues, the greens, and the yellows of the world. So if I show you with this little red robot there with his blue feet, we can see that working. This red robot has green arms, and the keep-on is bright yellow. But yellow can be a little bit hard to compute sometimes, particularly quite saturated with the lighting in the room at the moment. And I've added my own fourth feature, which is face detection. And I've done this because it's so easy with OpenCV these days. I'm going to get to habituation in a second, but for now we're going to talk about combining these four features together. Okay, and we do this in a weighted format to calculate a saliency map. So for instance, if I introduce the weight of motion and color, we see in the saliency map a bunch of different values, and we see these two maps combined together. We've also had a point appear in the world, and this little red point represents the most interesting region in the saliency map. And it finds the biggest region with the highest value pixels, so in this case it's my mouth, and it finds the center of mass of that region and says, that's what I'm interested in. So if I bring a robot, it should, excuse me, focus on this robot rather than on me. Even if I introduce the face weight a little bit, we still find that the most interesting thing is still going to be the things that move rather than my face. And the same with skin tone, even if I introduce a little bit of that, should still focus in on the robot because they have the highest weights. Okay, and so there's a couple of parameters driving these three, particularly the motion map and the color map. There are thresholds which allow you to set the color detection and the motion detection. So I'm just going to pick red for now, the color map, because it's easy this way. There we go, so we're focused on red. And this little guy is going to be my demo. And so this in itself is actually very powerful. It's quite a simple model, but you can do a lot of it. And what they do, or at least what Brian Scazzolati and Cynthia Beazeal do, is they manipulate these weights with different tasks in mind. So their robot Kismet is either playing, it's looking for a caregiver, it's wanting to engage in interaction with people. And so for each of these different modes, they introduce different weight combinations. And that drives how the robot behaves during these different modes, essentially. Now, because this is running on a desktop machine, we can't show it running on the robot and can't show the habituation map and what this really does, but I'm going to talk through it quickly. And so what the habituation is it's a bias for where the robot's going to look in the field of view. Now, like I said earlier, robots look around the world, yeah, very much like children look around the world. They're never fixed on one particular thing for a very long period of time. So what you can do with habituation is actually cycle through. Imagine the robot's looking at me now. After a while, the habituation is going to start pushing the attention point to look somewhere else, and that's going to drive the robot's gaze. And we do this driving with a fovea as well, okay? And so points which are within the fovea are of interest, and as soon as they pop out, we want the robot to fixate and center on those different points. And so this habituation cycle is going to run, and every time we move the robot's head, we effectively reset it, like this. If we look here, I'm going to reset it again. Boom. There we go. And there's a number of parameters which are driving the habituation. Let's just turn the cycle period off. And it's essentially a 2D Gaussian field. And as time goes by, it starts like this, and then it goes away, it decays, and then turns to a negative decay, forcing attention to the edge of the screen rather than to the center. And that's eventually when the robot decides, actually, there's something more interesting over there, or there's something more interesting over there. Now the parameters are, we have an X offset and a Y offset, so we can move it around the screen. And we also have sigma values as it's a Gaussian. And we can make it really big, and we can make it really small, okay? Now this is going to be better demonstrated in the follow-up video, which you can see the link for downstairs. Oh, not downstairs, but down here on the screen. And for now, I'm going to leave this at this. It's just a quick run through of what the parameters do, and I'll talk more about how they really interact and work together when I show it on the robot. Okay? The code is available for download. Again, see the description of the video to download the code. But for now, I'm going to end this video, and I draw your attention to part 2. Okay? See ya.